I'm going to explain first problem of the problem set, the easy sum. Step 1. You start with the set called n. It contains all whole numbers from n to 1. For example, if n equal to 14, then a set is 14, 13, 12, and 2, 1. Step 2. Take the first element of a, which is n. This will be your numerator. Now, divide this numerator by given denominator, m. Let's say m equal to 5. For 14 divided by 5, the remainder is 4. Label this remainder as R1. Step 3. Create another set called B with the same number of slots as element in A. Place R1 in the first slot of B. Step 4. Now take the next number in A, which is n in n minus 1. Use the same denominator m. For example, with 13 divided by 5, the remainder is 3. Place R2 equal 3 in the next slot in B. Continue this process for all elements in A. Step 5. Once B is filled, sum all these elements. The total is your answer. That's how you solve the easy sum problem.
Let's talk about pairwise sum and divide problem. Let's solve this problem step by step. First step, find all pair of numbers. Look at all possible pair in the array where the second number is bigger than the first. For example, from a equal 2, 4, 6. The pairs are 2, 4, 2, 6, 4, 6. Step 2. Use this formula for each pair. For every pair, ai, aj, we calculate. Result for the pair, sum of the two numbers, divide product of the two numbers. Let's try one pair together. 2, 4. 2 plus 4 divide 2 multiplying 4 equals 6 divide 8 equal 0.75. Then round it down, so 0.75 becomes 0. Step 3. Repeat for all pair. Do the same for the other pair. For 2, 6. 2 plus 6 divide 2 multiplying 6 equal 8 divide 12 equal 0.666. For 4, 6. 4 plus 6 divide 4 multiplying 6 equal 10 divide 24 equal 0.416 equals 0. Step 4. Add the all results together. Finally, add up the rounded down result. T equal 0 plus 0 plus 0. Thank you.
Problem 3. We need to calculate the sum of I to the power of n mod 100 for all I from 1 to k. K is the range of numbers. N is the power to which each number is raised. Steps. First step is start with sum equals 0. Second step is for each I from 1 to k. Final step is print the sum as a 2-digit number. As an example, k equals 3, n equals 2, 1 square mod 100 equals 1, 2 square mod 100 equals 4, 3 square mod 100 equals 9. Sum equals 1 plus 4 plus 9 equals 14. So the output is 14.
Let me explain the problem of scalar product step by step. Imagine we have two vectors a and b, each with the same number of elements. The goal is to compute their scalar product, which involves multiplying corresponding elements from the two vectors and then adding up the result. We can use for this formula for that. Scalar product equal sigma ai by bi for I equal 1 to n. Here's an example. Suppose a equal 1, 2, 3 and b equal 4, 5, 6. First we multiply the first element. 1 by 4 equal 4, and then second 2 by 5 equal 10, and finally 3 by 6 equal 80. Then we can collect the result in a set, and adding these together give us 32, which is the scalar product of a and b.
Problem 5. First, understand the problem. We are adding numbers in a series. Sn equal t1 up to tn. Each term th equal h to the power k, where h is a number from 1 to n and k is the power. After adding, we find Sn mod 10 to the power 9 plus 7, which keeps the result small. Solve step by step. Start with s equals 0. For each h from 1 to n, compute th equal h to the power k. Add th to s and take the mod 10 to the power 9 plus 7 to immediately to avoid the large numbers. The result is Sn mod 10 to the power 9 plus 7. Example. For n equal 4, k equal 2, compute terms t1 equal 1, t2 equal 4, t3 equal 9, t4 equal 16. Then add them. S equal 1 plus 4 plus 9 plus 16 equal 30. Take the modulus. Sn mod 10 to the power 9 plus 7 equal 30. That's how we solve it. Repeat the step for each test cases.
Explain the Big series Gn step by step. First step was definition. The series starts with two base cases, G is 0 equals 0 and G1 equal 1. For n larger than 1, the formula is Gn equal 2 multiplied with Gn minus 1 plus Gn minus 2. Calculation. The second step for calculations. Using these rules, we can calculate G2 equal 2 multiplied with 1 plus 0, the equal value is 2. G3 equal 2 multiplied with 2 plus 1, the answer is 5. Continuing, we can find the G10 value 2378. And we go to advanced functioning. Next, we define the LPN which combines coefficients C1 with terms of Gn. For example, using C0 equal 3, C1 equal 1, C2 equal minus 1, we can calculate L46. Comparing sums. Finally, we examine sums like S1P and S2P. For P equals 4, S1 4 equals 7, and S2 4 equals 3, showing how to coefficients reveal patterns in series. Step by step process illustrates the beauty of recurrence and how it uncovers deeper mathematical relationships. Thank you.
In the circular number game, a fascinating mathematical problem and combines logic, computation, and patterns. Here's how the games work. In each round, one child adds the sum of their neighbor's numbers to their own. This continues for m rounds, moving sequentially from one child to the next. For example, if 5 children start with the number 1, 2, 3, and 4, 3, 4, and 5, child 1 would first add their neighbor's number 5 and 2, making that total 8. This is where mathematics come to the rescue. We use transition matrix to model how each child's number change based on their neighbors. By applying matrix exponentiations, a fast algorithm, we can protect the outcome from any number of round efficiently.
Problem 8. Counting summation. Asks how many 2 by 2 matrices result in zero solution. Using Gaussian elimination with modular to method. The process involves. First one is setting up 8 possible matrices with specific rules. Second one is applying Gaussian elimination to find the rank of each matrix. Third one is calculating the number of solutions use the formula. Fourth one is checking for matrices with exactly zero solution. The result is that none of the matrices have zero solution. The final answer is 13.
Double summation structure integrates all the pairs I and j. The outer summation loops over I from p to r minus 1 and the inner summation loops over j from I plus 1 to r. For each pair I and j, we calculate the XOR of elements and index I and j in array A, represent as the XOR of AI and AJ. Then the result is XOR with the value of k. The output of each calculation is added to a cumulated total called KPR sum. Finally, this process given the result by summing up the XOR valued for the all valued I and j pairs within the range, as shown in the example for k equals 1, p equals 1, and r equals 3. The output was calculated as 5 by adding all XOR result for the pairs 1, 2, 1, 3, and 2, 3. This ensures the result compute all the pairwise interaction effectively.
The solution approximates the sum of an infinite series by evaluating a large number of terms. The series involves the constant defined in the context, and function qx is derived as a x plus 0 multiply x plus 1 with px equal 1 when b equal 1. The series is expressed and differences fn minus 1 over successive terms, ultimately simplified to fn minus f0, which evaluate to 1 when computed. This method leverages the convergence of the series for practical applications.